washing colored light. It felt like spirits had awakened me. This carnival of animals had taken me. They danced around me and they took my hand. Whispered, close your eyes and understand. And when I felt the change, it startled me. This carnival of animals is part of me, part of me, part of me, part of me, part of me.
All right, good morning. This is Wallaber. I'm working on my physics-based gymnastics game called Pro Gymnast. I did a stream last night where I started working on trying to get some extra motion in the hair. Let me just adjust the volume here a little bit. Okay, so where I left it yesterday is I had started creating a plan here for how I can have a sequence of bones, essentially, that I can then try and add a little bit of a simplified physics simulation to, but in a way that I've worked out that hopefully will meet the needs of my game, where the character is constantly flipping and rotating and stuff. So first thing I wanted to get going on is I want to be able to visualize these bones real quick. So we're gonna do just like a wire cube, I guess, for them. Okay, so Hit Gamey, what's up? Happy Friday, indeed. So I've been, I had a stream late last night, where I started investigating giving some secondary motion to the hair of the avatars, which I think is worth doing. And so, okay. And so now I'm going to start trying to make some simple little physics code here for the hair. So this should be this times 0.5, and then I want to draw a wire cube at the half point. I've been playing with box casting. Oh, cool. Yeah. Box cast, capsule cast, sphere cast. I use sphere cast quite a bit just to do kind of like a thick ray cast. But Gimme, I think I recently followed you on Twitter, if I remember correctly. What kind of game are you working on right now? This should be... Need to confirm if another car is in the next lane. So box, oh, that's cool. I see. So you sort of take a box that like represents the car and then cast it out left or right. Makes sense. I suppose in that case you could also just take a box and just slide it over and do an overlap. You take 911 calls and then have to chase down suspects. Oh, was this were you mentioning somewhere that it was like a game jam game that you're still working on? Okay, now we're gonna have to give this I think you know that Crazy Taxi is one of my favorite games, so I approve wholeheartedly. Let's see, the rotation of this thing is going to be just this. I'm not going to worry about scale for now. Okay, so based on that, this, oh, Yeah, actually, let's do this instead. No, I don't like that. I guess I have to do it this way. For this to work, though, things go off in a weird direction. We don't have an easy way of getting the other angles. We're just going to cheese this for now then. Let's just do this. We know it's in the X direction. Okay. Just see if that code basically works. There was kind of a similar game to Crazy Taxi in the arcades for a while there where you were an ambulance driver. So it had an extra kind of element where you had to drive carefully, basically. Okay. What's going on here? Uh-oh. Oh, shoot. Infinite loop. So you gotta be careful with these linked lists. Okay. Let's kill Unity. Ooh, a bridge chase. That sounds cool. I guess that's why you need to know things about what cars are in what lane, right? Okay. Let's get back to the project. I think I've seen somewhere online that there's a way to, if you accidentally create an infinite loop in your code in Unity, a way to catch that, as opposed to just having to kill the entire task of Unity. But I've never really looked into it deeply. Alright, well, hopefully this got rid of our infinite loop. Okay. Hoping to have something on YouTube later today. Cool. I want to check it out. Make sure you tweet or something so I see it. Alright, come on. Come on. Unity, you can load back up. Okay. Come on. This is like strong incentive to be careful to not write any more infinite loops today, which I'll have a chance to because of this data structure I've got here with this sort of like linked list. Okay, let's go back to our scene. Where is that going to be? Here. Here. Okay. Did I save this? I did. Okay. Cross your fingers, run it again. Alright, those are completely wrong. For the right size, their position is totally incorrect. Why is that? Oh, I'm double offsetting here. Okay. Alright, this should allow us to at least sort of see, visualize the bones. Okay, cool. Alright, so now this is going to be our chain here. So this is going to be like the root. This one won't move. But these 3 points here should be able to actually move and simulate. Okay, and so for that to work, that's because I'm going to have these endpoints. These are my world positions and world velocities of those. So let's start doing some kind of super simple simulation. Alright, so let's write out the steps here. I think what we're going to do is... yeah, we're going to try this with kind of a mixture of like particle physics and then some cheats, I think. Let's see if it works. So what we're going to do is we want to add gravity and integrate each particle. Then we're going to constrain distances. Then we're going to solve final hair positions, and this is going to involve one, place transform at rest position, or basically what we're going to do is we're going to calculate rest position in world space. Then we're gonna constrain the distance and angle. Then we're gonna apply the spring. Then we're going to orient transform to point at the world point position, and then move down the chain. Okay, so to get this going and testing, yeah, let's just do this first. So we're gonna say chain node n equals chain, and then while n let's just do gravity and integration. Okay, so yeah, so this, I guess we're gonna want probably like a maybe like a gravity scale. I don't think we want full gravity, but who knows? So let's make this a scalar. Okay, so then what this would be is the node's velocity is going to get physics.gravity times gravity scale times time dot fixed delta time. We probably also want to say that we're not, if not physics.auto-simulate, or we might actually want to, later we might make this a function and we manually actually update these at a certain point, but let's just keep it simple for now. Alright, so we're going to apply some gravity to the velocity, and we're just going to integrate. So that's just the position plus equals velocity times time. Okay. Alright. Then we're going to constrain to distances. So the way this is going to work... Oh, wait. Infinite loop check. n equals n dot next. Okay. Then we're going to loop through these again now. And this one is actually going to maybe take more than one loop. I don't know how much this step is going to matter because of this, because I'm going to do some stuff back here. I think this is the thing that allows a little bit of participation between the nodes backwards up the chain. So let's, we're going to want to have a value here distance constraint iterations. Some number. Okay. So then we go here. And we say for I equals 0, I is less than that thing, not that thing. Distance constraint iterations, I plus plus. And then in there we do something very similar, where we start at the chain, and then in this case, we need it to be not only that we're not null, and n.next node is not null. We're going to access both in here. Okay, so point A is n dot endpoint world position. Point B is n dot next dot endpoint world position. Okay. So then what we do, and the float dist is ends. Is it? No. It's the next one. Is n dot next dot endpoint distance. Right. So we're going from here to this node, and then to the next node. I want to make sure these two are the correct distance apart from each other. So now we need a direction. PB minus PA. Current dist is the magnitude of that. Okay. And then we can say move. The move amount is, we want to get to dist from current dist. Right? Yeah. So current dist plus x equals dist. So x equals dist minus current dist. And just double check that. So if we're currently 1 unit away from each other, but we wish we were 2 units away from each other. Yeah, that'd be 2 minus 1. That's a positive number. It says we need to increase our distance. Okay, so that's right. So now we're just going to blindly move these points, right? By the half distance. Yeah. So now we need to normalize the direction. And this is going from point A to point B. So that means we say PA plus equals, I guess what we do is also do this. We'll call this the half move, because we want to take this thing and we want to get half of it. Okay. So then PA is going to be dir times half move. And then PB is going to be minus equals dir times, I guess I don't have to double multiply this. I could multiply that out. Okay, that's going to move them. And it's going to move on to the next one, and then we're going to repeat this whole thing a handful of times. Now we should be constraining the velocity here as well. Right. Okay, so now we would be like, now what we want to do here is we want to take, okay, v dot a, which is going to be the dot product between the direction and the velocity of a. Oh, and by the way, we need to actually set these here. So n dot end world position equals PA, and n dot next dot end world position equals PB. Okay. So now here, what this will tell us is how much of world velocity is aligned with direction. And so here we have a thing going from PA to PB. And PA velocity is like some number, right? And we want to remove any element that's negative. pulling us away. So I think what I want to do here is go, I want to say anything that's less than 0, right? I want to min this with 0. We either get 0 or we get a valid negative number. Okay. Yeah. And then we want to say n dot end word vel minus equals dir times v dot a. Pretty sure that's right. And then we can do the same for b. So v dot b is going to be vector3 dot the direction, and then n dot next dot velocity. In this case, expecting a positive number, so we're going to say mathf dot max of this and 0. So if we're headed towards, we don't make any changes. If we're headed away, we do, and this is the same thing. N dot next dot not that. N dot next n dot next. Why is this not auto completing? Did I screw something up? Weird. Okay. Dot velocity minus equals dir times v dot b. Okay. So that, I believe, is going to remove any velocity component that's trying to pull this constraint away. In reality, like, these are fixed hard constraints. They want to stay this distance no matter what. So actually, I don't think I care about doing this part. I think I just want to do this. We're going to get rid of any velocity component that is pulling or pushing. Okay. Let's see if that's right. Okay, after this step, we should now be able to start visualizing these endpoints to see what they're doing. So let's go back here into our drawing. And so this is yeah. So I think while we're in here, we could be able to, we could say if node dot next node does not equal null, and we can say debug draw a line from node dot world position to node dot next node dot endpoint world position. Let's draw this in magenta. Okay. Let's see. Did I screw something up here? Do I have an infinite loop again? We don't here. And we reset it here. And we move on to the next node here. Okay, so I don't think I have an infinite loop about to happen. Let's find out. Okay, we're gonna, where should I put, I'm gonna put this down here, I guess. Get it out of the way. Okay. So what do we get if we run this? We get explosions? We get explosions! Okay. Alright, so let's figure this out. I bet it's my constraints. Let's just make sure. Let's comment this out for a second. Okay. Alright. Now let's pause it. Let's look at this thing right out of the gate. Okay. Okay, there we go. Those are our points. And they are just falling. Okay. Well, that part looks okay. It's highly likely I screwed up the velocity constraint stuff. So let's remove that for a second and look at what's happening. The other thing is I'm realizing, I think, that the first one, yeah, we have like an extra constraint, I think. So really what I want to do is I want to take this and I want to make this into a helper function. Now, distance constraint, ref PA, ref PB, dist. Oh, and then maybe what we want is like out dir, something like that. Okay, so then we would come down here and we'd have this little helper function, private void distance constraint, takes a ref vector PA, ref vector PB, takes a distance, and it has an out vector of the direction. Okay. So then this would be that. Okay. Da-da-da, da-da-da, da-da, and then we change those guys. Okay. Okay. So that I can use this here. Okay. Because I'm going to want another one up here, which is kind of a special case. Yeah. This would be kind of gross, but let's just do it this way. So in this case, vector 3 start A is equal to the n dot it's going to be transform dot transform point n dot root position, and then start B is going to be n dot end world position. Okay, and so then we can say distance constraint between start A, start B, and then n dot end world dist. Okay, out dir vector 3 start dir. Okay. And then we can't let the first point actually move. Although it doesn't matter because it's not getting saved anywhere. Because really what we want to do with this is we want to say n dot world position is now equal to start B. Okay. Okay. So let's look at this and see how messed up this looks. Oh, that means we're also going to want to draw down here. From transform dot transform point and node dot root position to node dot end world position, also magenta there. Okay. Okay. So this shouldn't let the points get too far away from each other, but the velocities are not being constrained, so this shouldn't be stable at all. Let's see. Yeah. Okay, wait, let's watch this again. But maybe I'm even screwing up just this part. Yeah, look at that. Boom! I'm moving in very wrong. Okay, so let's go look at my math. What's wrong with this? This is a line going from A to B. We get the current distance, CD. Dist is what we would like to be. Right? So let's say CD is there, and then we got our distance, which is what we want to be. We take this, we subtract this, so we get the difference. Okay, and it's going... Yeah, if it's positive... we want to grow the length. So I think I have these backwards. Yeah. Okay, let's double check that. Okay. So now we have some pink lines that can't stray, and they're just going to fall to pointing straight down. That's what we would expect. Let's try putting back in our velocity constraining here, which now I think that's going to work correctly. I guess I should also constrain the velocity up here for the endpoint. So that would be like... I want to dot the direction. I mean, I guess what I should do is actually put this into that function. Okay. Then we would be like n dot vel minus equals dir. Oh, there's no dir up here because it's called start dir. Times v dot start a. Okay. In theory, this shouldn't really look any different. I think. Woo. Okay, so something is wrong with that for sure. Let me think about this again. What I'm doing here is I'm saying, take the direction, so there's a line heading from PA to PB. We take the velocity of point A, we get the dot product of that, which tells us how much of that thing is on that line. Oh. Actually want to add it? No, I don't want to add it. What do I want to do here? Alright, I have this. I want to end up with this. Weird. I think I actually do want to add it. I need a way to like draw some diagrams on the stream so I can show some of this a little better. And like in this case, if this one is like headed this way, This one is the subtract case. This one is an addition case. Okay. Has to do with which way the direction, which way the line is expressed, I think. Okay, is this gonna make any difference? Whoa. That's not good. Well, that's true, because if we were... Oh, right, no, this should be a negative vector in this drawing I have down here. Yeah, maybe I'm just thinking about this wrong. Because this actually looks right. They should all be minus equals. Yeah, I guess, okay, so this is probably a case where I should be using like a Verlet integration or whatever, because right, because the actual resulting velocity is really just where we were and then to where we ended up. I could try cheesing that here. The easier way to do it, yeah, it would be to give them all a previous position. Because then what we could do is right here, we store that, then we constrain all the positions, and then we would actually loop again like this, and we would work out the velocities. So so this would become going to our new position from our previous position divided by time. Which in this case, we're not really doing much with that other than... Oh, whoops. Other than we use that to get our gravity and then to find out where we wish we were each frame. Okay. Or each update, I should say. Okay. Uh-oh. Did I screw something up? Oh, God, I did it again! Did it again. Terrible. Unity. Kill. Can't believe it. Ugh. I won't normally write things with these like linked lists out things, so I gotta remember to be diligent. Okay. Let's get the hub back up. Okay. So once we get this basic thing going, then we can try doing our actual springs to try and get this thing to try to go back to its rest pose, but with some limitations. And we're going to go back here to our scenes. Air physics test. Okay. Okay. Uh-oh. Still screw something up there? Certainly did. Where's our pink? What have I done? Oh. Good lord. Okay. Okay, we got pink lines back. Pink lines are falling. Ooh, cool. See, now they're keeping some momentum, which is what you would expect to see. We got ourselves a little pendulum happening here. We're going to want some damping and stuff on this, I think, eventually, but that's cool. And I guess if I set gravity scale to 1, the whole thing would kind of feel more downward pull. Right? Crank it up. Essentially speeds up the oscillation. Okay. Alright. Cool. Oh, now we can actually do our plan here. So we're going to have another loop over our chain. Okay. These steps belong in here. Don't forget this. No, this is the move down the chain command right here. Okay. So what are we doing? We need to get the goal position in world space, and in this case what we're going to do then is we're going to use right, we're saying relative to our previous node, right? Right. And if I have this remember correctly here, we say this is the transform for that node. Okay. So it should be safe, I think, right here to say n dot node transform dot local position is equal to n dot root position, and n dot node transform dot local rotation is equal to n dot root rot, right? So that should place us offset from our parent where we expect to be, which now means we can say our rest point world is equal to n dot node transform dot transform point n dot bone bone main axis times n dot distance. Oh, and we can get rid of this because we made this kind of a global setting for this whole chain. Okay, so there. Now, just to test what? Now we're going to... Okay, this is where then we would constrain. We're not going to do that yet. Now let's try applying a spring. Okay, so what we got to do in here is we got to pass in our n dot world position and our n dot velocity. Okay, and we say where you wish you were is rest point world. Okay, how much time is passing? Time dot fixed delta time. And then we've got a frequency and a damper. After this step, world position and world velocity will have updated. Oh, I need to do this in 3D, so I'll do it the way I like to do it, which is like this. Oops. Like that, and then we say float p is equal to end world not I, and float v is equal to n dot this I. So then we can just pass in position, velocity, and the coordinate we want there, and then after that we can go back to here and say n dot end world position of I is equal to p, and n dot end world velocity of I is equal to v. Okay. So in theory, that's going to start to spring that position back. Okay, so then what we want to do is we want to figure out how to point our transform at this new position, and I believe what we're going to do for that is this, which is vector 3 dot from it's quaternion from 2. So we want to go from the want to go from rest point world minus n dot node transform dot position. We want to go to n dot end point world minus n dot node transform dot position. So this should say, what do you need to do to rotate from the rest pose to the current thing? So then we could just say n dot node transform dot local rotation is equal to n dot root rot times additional rot. Okay. Okay. Oh, hey, Bobo Rosso. Hey, do you think you could add facial hair to the game? Oh, actually, I probably could. The system I'm using does support it. I just need to see what options I actually have in terms of assets, and then add that into the avatar editor UI. But that's a good reminder. I'll write that down. Okay. Okay, so is this going to do anything? Let's find out. Or is it going to totally cause things to explode? Could do any of those things. Could work perfectly. Could cause explosion. It gave me feature creep, yeah. Facial hair feature creep. Should be pretty easy though. But maybe not, you know, may not make my cut for a 1.0 important. Whoa, okay. So this has got a bad feedback loop in it. And I think that's because of this. Do I have to do these in the other order? I can never remember the order I need to multiply quaternions. Or it's possible that that logic there is just wrong. Okay. Okay, yeah, see, this is just totally wrong. See, we're producing rotations that are just messed up. So why is that? Okay, if I don't do this, then what we should see is that the magenta lines just sort of drape below the blue lines, but the blue lines never update, if I'm thinking about this correctly. Okay, yes. Right. Alright. And if I crank this up, right, they droop farther. Okay, so my problem is I just have this is wrong. Oh god. Dang it, there's a sign wrong there. Okay, so if that was all it was, then I think my initial, if I remember correctly, the way you do quaternions is like, they go in kind of reverse order. So the one on the right here, additional rot, is like the first rotation that happens, and then the second one happens after it. In this case, I'm actually not sure what order it should be in. It might actually need to be the other way around. Is this going to be still off? Ooh, okay. Yeah, it looks like it's backwards, see? It's going the wrong way. It's counteracting gravity. I think that's just this thing I was just talking about. So if I do this, this says, yeah, we want to like do the normal rotation, and then we want to add this additional rotation into the mix to get us pointing at the final point. Okay. Okay, so now if I crank up gravity. Oh, interesting. That still doesn't seem right. Okay. Because I would expect right now that the bones should be pointing, should be lined up with the magenta lines. And really, actually, I'm gonna need to do some improvement here to make these blue lines actually show the rest position or whatever, but let me think about that. Yeah. So right, from direction to direction. Now this is in world space. That probably matters. Right, so we actually maybe don't want to do this in local space. We may want to do this in world space, where we say n dot. Because up here, we got ourselves a rotation that's our rest pose. So this would be something like that. Is that right? Rotations are always just at the edge of my grasp. Okay. What happens if I crank this up? Hey! Hey! Look at that. Now we should be able to, within reason here, look at that. Move this thing around. And it's trying to get to the, if I set gravity to 0, right, it's going to be like trying to keep that rest pose, but it can be disrupted by movement. Now it's a little hyperactive, but that's okay. We can probably add some damping and stuff to this. This is pleasant. This is what we're looking for. And now in theory, see what I can do is I can go look at this and say, okay, I had set up this initial chain to be sort of like this weird shape, right? Let's make it something different. Like let's say, yeah, first one goes out like this. Okay, let's make it a straight line. That should be as simple as doing this. Okay. Right, so there, now it's a straight line going in some weird direction, but it's a straight line. And this should work pretty well, even if you, like, rotate. There may be, like, a max speed there, see where it, like, the world positions don't realize they're getting yanked around. So I might want to, like, substep this or something. Because we do have some pretty fast rotations in the game. We're not going to have super long chains like this. Okay, so that's pretty cool. Now let's imagine it's like a... Let's simplify this. Let's see, which way is this facing right now? Well, let's just imagine that these are like a kind of like a little curved piece of hair, like a ponytail or something. So this should now look like a curve, like that. That's its rest position, right? Ponytail hanging off the back of the head. And we move the head. Right, and so we're getting some kind of like unrealistic motion. And I believe the main cause of that is is that we're only really calculating the constraints one direction. But we're probably going to want support for some velocity damping. That, I think, is fine as like a global thing. And then we always get this thing where if you say the word damping, you would say, oh, if I pass in a 1.0 to this, that means I want to completely dampen the velocity. Which then means you gotta do a 1.0 minus that or whatever down in the code. But if I call this inertia factor, right? And we're gonna say that this should be like 0.95 F or something. this number is just a number we can use to calm down the velocity. Where are we going to do that? We're going to do that here. Times equals that. And then I guess this number really should be range. Okay, look at that. Okay. And let's look at this again. Okay. Alright, and if we crank this down, yeah, it should just be kind of like more molassesy, right? Where it just really wants to drag behind whatever the movement is. So if you turn the head or whatever, see, it's like that. So between that number and the physics springs and the gravity scale, we should be able to get this behaving in a way that we're happy with. The one thing this is not going to do is it's not really going to have, well, I guess if I did this. It's not going to have a ton of like centrifugal, force where it's sort of like as you spin fast, it like points straight out. In fact, there's like a weird thing probably where if you spin fast enough, it sort of collapses in on itself. But we already simulate the physics quite rapidly in the game, so hopefully we can get this to work with a combination of the right numbers and everything. Okay. Let's see, should we try looking at it on some hair? I believe we can do that. I believe if I go get this, I bring that into here. Let's turn this off for a second. Go look at this. And if we walk our way into the hierarchy here, here. So this is what we would want. We would say on here we're going to add a dynamic hair chain. The first one's going to be chain 1 left. Okay. And everything else the same. What happens if we hit run? Okay, the left hair got some weirdness. Yeah, why is it sort of like folded down like that? Okay, so yeah, what is the deal there? Should be these bones here. Okay. Now what if we hide the hair? No gravity. Okay, so gravity is causing a problem. It's probably because, oh, I think I know what it is. Yeah. Okay. So we're not applying a spring to this very first point in the chain. And so since it's just getting yanked down by gravity, it's just like gonna point down and then the rest of the math all gets off. See, if I set this to 0, And I turn this back on. And we do things like rotate the head. Okay. We're getting something. But see, I can't have any gravity affecting it right now. Well, I guess if I set it sideways like this and then crank up the gravity, it'll look okay. But that's gonna look bad when I come back. It's just gonna fall straight down because we're missing a spring. Okay. We're getting somewhere though. It's weird that... Oh yeah, like a weak gravity actually looks the worst. I get why that is. Okay. So we're gonna have to fix that. That should be pretty easy though. I think it's just a little bit of special logic for the first node. Actually, yeah, I gotta look at that more closely, why that's the case. But yeah. Okay. Oh, this is a 0, so why is it? Yeah, not loving that sort of wiggle that's showing up. Which may be related to... Take this out. Alright, I was also going to constrain the distance and the angle, which I haven't done yet. Okay, I'm not sure how much I can evaluate this right now with that first link in the chain kind of busted. Which also may be related to negative gravity. Wow, look at that. Okay, so we're getting somewhere. Alright, so we need to work out, is there a bug here with here? Right, or is it just simply that we need stronger springs? I'm not sure if I have a bug or it's just that I need good data in here, which is that like wherever I make this thing down here, yeah, one thing too is we could change this to be slightly over damped and like crank this up. Which I don't think is how we want this to work, but let's try something. The thing I should test is if this will actually work on 2 chains at once. Let's do that right now. So let's go like this. Copy, paste is new, paste is new, and then chain 1R also gets a chain. Now we should see both pigtails got their chain, so that's cool. Okay, so this is a much stronger stronger springs now. They don't look that great. I gotta figure out how to get rid of that jitter. Okay, I kind of get why it's happening. What happens if I move this thing? That looks pretty cool. I feel like I'm gonna tune this where I don't have like hyperactive amount of movement. I just want some. So in this case, that would entail changing this, but also eventually yeah. Yeah, I don't like that. So I think we're going next we're going to need the ability to properly set these per node, and then I got to implement this, which I think will go a long way. For something like ponytail, I can have that first node have a very narrow cone of max angle. That's like, it can't suddenly turn and just go into the head. You know, it's got like a small range that it's allowed to rotate. And then the later ones can get bigger so they can flow. So I think tomorrow, that's where we'll start. Is we need to do this. Okay, and then we need a way need fields to control spring factors over the chain. Okay, cool. That was a solid chunk of progress today. We basically wrote 239, not really, but 200 lines of code. Got ourselves some semblance of a simulation working with our own method here that I like, which is kind of half physics and half not, but I think is going to give me more options here to control how I want this thing to behave when the gymnast moves around. That's cool. Tomorrow is Saturday, so I'll have maybe like 2 hours or so in the morning to keep working on this. All right. Thank you very much for tuning in, and be back tomorrow.